Welcome back to Calculus 3. So today I have to finish up vectors. Remember that we started learning about vectors, and we did already a few things. Remember that a vector is some mathematical object that has two characteristics. There. It has a direction, and it also has a magnitude. So the length of the vector and the direction of the vector is everything that a vector has. And then when we write in coordinates, all our vectors are going to start at the origin, but no vector is anchored at any given point. It's just for the coordinate system, we anchor them at the origin. So remember that we've learned how to add vectors. So if I have a vector and another vector, what I do is that I put them starting at the same point, and then the addition, for the addition, I do the parallelogram law. I complete a parallelogram, and then the addition of u and v will be the diagonal, right? And we also learned that we can do subtraction of vectors. So if I have u and I have v, to see where u minus v is, for example, what I do is I use my scalar multiplication of vectors to find minus v, and then I add u and minus v, so I complete the parallelogram here, and u minus v will be that. And you see that it coincides with the vector that goes from the end of v to the end of u. Okay? So where would v minus u be? Notice that v minus u is minus u minus v, right? So it is actually just in the opposite direction. So the vector that goes from the end of u to the end of v, this one is actually v minus u. Okay, so let me put this one here. This is u minus v. In the other direction is v minus u. I always forget in what direction I have to go if I do that parallelogram law. So that's why I always try to remember it in this way and not in trying to figure out in what direction should I go, from here to here, from here to here. Okay? All right. So we can do this in coordinates. As I said, addition of vectors is component-wise. So let's figure out, first of all, what is 2v? 2v is twice minus 1, 1. So that is minus 2, 2. And then what will be u plus 2v? That will be 2, 3 plus 2v, which is minus 2, 2. And I add those component-wise. So it's 2 minus 2, 0, and 3 plus 2 is 5. Okay, so that's u plus 2v. U minus 2v would be 2, 3. And I have to scale by minus 2v instead of by 2v. So I'm really adding the negative of that one. So I'm adding this one. So what I get is 4, 1. All right? And if you draw these, you'll see that these sort of parallelogram laws, they actually work in practice when you do addition in coordinates. We can do the same thing in 3 dimensions. Addition of vectors is exactly the same. It's component-wise. So u plus v will be 2, 3, 0 plus minus 1, 1, 2. And that will be coordinate-wise. 2 minus 1 is 1. 3 plus 1 is 4. 0 plus 2 is 2. Okay. Now, we can also compute lengths of vectors. The length of a vector is the magnitude. So if I have a vector, I'm going to compute the length. I'm going to call it that. Sometimes you'll see it with a double bar. That is the length of the vector. And that is the magnitude. Remember, the vector has direction and magnitude. So what is the magnitude of a vector? In 2 dimensions, we have seen in 2 and 3 dimensions what are distance formulas. So if I have a vector here, then this vector is going to have coordinates. if this is the vector u, and the vector u is, let's say, x comma y, let's call it, there is u1, u2, then this length here from here to here is u1, and this length from here to here is u2, and then you can use, well, Pythagoras' theorem or the distance to this point from the origin to figure out that the length will be the square root of u1 squared plus u2 squared. And if I'm doing this in 3 dimensions, if I have a vector somewhere in here, which is something like this, there's some box, and it's going from the origin to the corner of the box, and this vector is u1, u2, u3, then the length of u will be the length from the endpoint to the origin, which we know how to compute. That is the sum of the squares of the coordinates. Okay, so we can do that. So for example, let me find the length of a plus b. So a plus b, first of all, what is the vector a plus b? Is 403 plus minus 215. That is 2, 1, 8. And therefore, the length of the vector will be the square root of 2 squared plus 1 squared plus 8 squared. So what's that? 64 and 468, so the square root of 69. Okay, and you can do yourself a minus b, see what the length is for that vector. There's all sorts of properties, algebraic properties that vectors satisfy. We're not going to, I don't think we're going to get into much of this here, but for those that are in linear algebra, we are going to start, when you go into linear algebra, you start from vectors, from this idea of vectors of length and magnitude, or direction and magnitude, look at all these properties, and then what mathematicians do is, let's extrapolate this to a definition of something called a vector space, and then many different things can be vectors because they satisfy the same properties. For example, polynomials with real coefficients form what we call a vector space, and polynomials, you can do addition of polynomials, you can scale polynomials. They satisfy all these properties, and we can do all sorts of math like we do in linear algebra, but in other things that do not look like vectors in space. So the definition of vector that I gave here is some very basic definition that later we'll revisit when you take linear algebra with me or without me. Okay, so we, as in actually in linear algebra, to express vectors, we do everything in terms of a basis. So when I write a vector, that a vector is the vector, say, 2, 3, 5, then we know what that means. I have to go 2 units in the x direction, 3 units in the y direction, and 5 units up in the z direction. That is telling me coordinates with respect to a Cartesian system that we have chosen because it's convenient, because all 3 vectors, all 3 axes are perpendicular. It's really convenient. But sometimes, depending on the context, if you're working in some physics problem, you might not want to choose those axes, and you might want to choose some axes that are at some tilt. Or you might want to choose axes that are not even perpendicular because there is a plane that is moving in one direction, a boat that is moving in another direction, and you want to use those as your axes, x and y, and z is some other direction, and you might want to put everything in terms of a different coordinate system. And in any case, so the system that we have chosen is based on these standard basis vectors, the I, the j, and the k. The I would be the 1, 0 vector or the 0, 1 vector for j in the 2-dimensional system. In the 3-dimensional system, I refers to the vector 1, 0, 0. j to the basic vector in the y direction of length 1 in the y direction, and k is the basic vector of length 1 in the z direction. And then we can write every vector in terms of I, j, and k. For example, this vector right here would be 2i plus 3j plus 5k. And in that notation, it really reflects the move 2 units in the I direction, move 3 units in the j direction, move 5 units in the k direction. And we can do all these operations of vectors either in coordinates with these parentheses or brackets or whatever, and then we can do them also in terms of the I, j, and k. So let me find, for example, the length of the vector 2a minus b. So first of all, what is 2a? That will be twice 4i plus 3k. So I scale that vector, just multiply the coefficients. So this is 8i plus 6k. Now, what is going to be, let me actually do it first by hand. What is minus b? That will be minus 2i plus j plus 5k. So I scale that in the, it's the opposite vector. So this is 2i minus j minus 5k. And then I can add them up. 2a minus b will be, well, 8i plus 6k and 2i minus j minus 5k. And how do you add? You just add apples with apples and oranges with oranges. So i's with i's. 8i and 2i gives me 10i. There is no j on the first vector, so this is just minus j. So I'm just going to put, instead of plus minus j, just minus j. And 6k minus 5k, I get k. And that's my solution. Please do circle, square, do something to highlight what your solution is in your work. All right? Oh, but that was not the problem. The problem was actually find the length of this vector. So now what is the length? The length will be the square root of the sum of the square of the components. So this will be 10 squared plus minus 1 squared. That will be just 1, plus 1 squared. So that even I can do. I think that's 102. So the square root of 102. So that was really not my final answer that I had circled. This is my final answer, the square root of 102. There are lots of applications of vectors. So here is one. I want to move on to the dot product, so I'm not going to solve this problem here. But actually, I spent my day yesterday recording this video. So there is a video solving this problem on the YouTube channel. So you can go watch that one instead. But there is many physical problems, many problems from engineering that have to do with, for example, you have several velocities. There's a current of one sort, some drag, some engine. And those are all going to give you vectors. And at the end of the day, you want to know what's your vector, and then you have to add them all up and see where you're going. And if you want to go in one particular direction, if you have control over one direction, you can move that around. So in this problem, the question is that I want to get here, and to move in that direction, actually, we're going to have to beat the current of the river at some angle so that if we're moving in a straight line, we end up dragging sort of directly to the dock. And you can see the solution just using vectors.